Hi, so today we're going to be solving Laplace's equation, and we're going to be solving it in spherical coordinates. But of course, as always, first of all we need to look at some previous results that we will be using, which will make our life much easier and the equation actually really nice to solve. So well, first of all we need to know what the Laplacian in spherical coordinates is. Well, this is an expression. But in this video I'm not going to be deriving any of these results or proving them. I'm just going to assume that they're true, and in fact they are. In other videos I will make some more explanation, more in-depth explanation and more rigorous about all of these things. But well, for now let's just explain it real quick and get on with the actual problem. So well, Laplace's equation, the Laplacian operator is defined as this in spherical coordinates. Well, this dot here just represents that that's where our function could be. Notice that I have not written any function here, just the operator by itself. So well, that's where our function would be. Of course, this function has to be nice enough so that we can take derivatives and everything. But of course, we're assuming that. Now, Euler's equation. Euler's equation is a really nice ordinary differential equation because we can actually solve it analytically. And this is the form of the equation. It's just x squared times y double prime, y is a function of x, of course, plus some constant alpha, which belongs to real numbers, times x, and again y prime, plus beta, which is another real number, and well, times our function. And this is equal to 0. To solve it, we are actually going to be proposing a solution of the form x to the r something. X to the r. And r is another real number. But let's not going to get into too much detail now. We'll see afterwards how it's done. What does this equation mean? Well, as we'll see afterwards when we propose this solution, this is the initial equation we have to solve in order to get our general solution, which could be given by this expression. And this general solution, yes, has two constants, C1 and C2, which also belong to real numbers. This just means that we're taking a linear combination of this first solution and this second solution. You see afterwards how all of this works. Now, the most important part is Legendre's equation. And this is actually the hardest part to prove and to derive the formula and everything. And I will make a separate video about it. But well, for now, let's just say that we have this differential equation. And we have that our x moves only in the range -1 to 1. And we're going to impose that it doesn't actually get to those 2 points, but it's actually on the open interval. And the reason for that is that we want to expand the solution in a series expansion. I'm not going to be doing it again here, but just so you know, we're going to do a series solution around x equals 0, and we need that x equals 0 in this case is an ordinary point. And for that, we need that x moves in this range, because that is the radius of convergence of the series around that point. Now, alpha, it actually can be a real number, any real number. Nevertheless, the solutions we're going to be looking for are the ones that in which alpha is a non-negative integer, that is 0, 1, 2, and so on. Notice I have called it n because it's really common and usual to call n these kind of sequences, like 0, 1, 2, 0, so I'm just going to call it n. But just bear in mind that alpha can be any real number. We are just taking the restriction that we are using this kind of alpha. And the solution to this differential equation is Pnx. And what is that? Well, Pnx, of course, let me just do a quick comment here. Again, remember, x moves from -1 to 1, okay? Now, what is Pn? Well, Pn is what's called Legendre's polynomials. And the n denotes what order the polynomial is. Now, if you look real quickly here, when we solve Legendre's equation and everything, we actually get this solution, these Legendre polynomials. And a really nice formula to get them, to get these polynomials, is what they call Rodrigues formula, or Rodrigues formula in more of a Spanish accent. So this just tells us that, well, Pnx is just 1 over 2 raised to the nth power times n factorial, and well, the nth derivative of this term here, which is just x squared minus 1 raised to the nth power. Remember, n is can be 0, 1, 2, 3, and so on. From this formula, we can actually get another relation, which might be useful in some other cases, but well, this is another way to generate these polynomials. and it is just 1 over 2 raised to the nth power times this sum here. Well, notice that I have written here that this term here, these weird brackets, are nothing but the binomial coefficient. And it is defined like this, n factorial over k factorial times n minus k factorial. Okay, so well, some of these things might seem quite strange at first if you have not studied them, but when I make videos about them more in depth, you see that they are actually pretty straightforward to understand. So now that we have already getting all of this out of the way and we're more or less on the same page, let's get on with the problem. So what do we want to do? We want to consider this equation right here. Let me just write a little better, yeah. This equation right here. And it is Laplace's equation in 3 dimensions. Okay? What this means is that, well, we have some function here and we take its Laplacian or Laplacian and it equals 0. What does this actually come from, or how does it appear in physics or in mathematics? Well, in physics it appears whenever we consider a region of space in electromagnetism where there is no charges. I would derive this here, let me just derive it from Maxwell's equation. Well, in electromagnetism we have that these four equations govern the behavior of charged particles. So we have that the derivations of E is equal to, it's equal to some charge density over epsilon naught, which is the vacuum permittivity. Well, this just means that the scalar sources of the electric field are charge densities, point charges. Well, not just point charges, but as I said, charge densities, distributions of charges. Now here there are no scalar sources of the magnetic field, that's why its divergence is 0. Now if we take the current, well, we have that this is just the usual Faraday-Lenz law. The curl is just negative the partial derivative with respect to time of the magnetic field. This just means that a very magnetic field creates an electric field, and likewise the curl of the magnetic field is just, well, mu naught, which is the vacuum permeability, times our conducting current, plus mu naught times our new generalized current introduced by Maxwell, which is called, what was it called? Yeah, this displacement current, which is just epsilon naught and the partial time derivative of the electric field. I'm not going to explain them into too much detail now. I'm just going to do a quick derivation, and well, we can actually define the electric field as, well, minus the gradient of some scalar potential, which is the electrostatic scalar potential, minus the time derivative of some vector potential. And this vector potential just has the property that, well, the curl of it is the magnetic field, and this just comes from this fact here, that the divergence of any curl is 0, so well, we can actually define this and this will hold. Well, just real quick, in our case we are considering that there's no magnetic field, so this goes to 0 because we're assuming that B is 0, okay, in our case. So this, we really do not care about this, so well, this also just goes to 0. This goes to 0, so we don't care about it. We really just care about this part right here. That's the only thing we care. And this would be assuming also there's no currents, and well, that the electric field doesn't vary with time. So well, as you see, we have simplified everything a lot. We have just getting rid of the conducting current, getting rid of the magnetic field, the time variation of the electric field, and just say that, well, we're just going to stick with this. This is more of an electrostatics problem. So, well, if this is 0, well, of course, we don't even need this right now. In fact, more accurately, we could say that A is 0. This would imply that, well, B is 0, just. And we just, well, it's just the same. But this is a bit more accurate. So really what we have is that E is equal to the negative gradient of some scalar potential, which we will call phi. Notice that this is phi. So let me just erase all of this real fast, and we'll see just where Laplace's equation comes from. If we substitute this into this equation, which is Gauss's equation for the electric field, we get that, well, this is just the divergence of some negative gradient, and this is equal to the charge density over the vacuum permittivity. And well, the Laplacian is actually defined as, this is the vector Laplacian, is defined as this, as the divergence of some gradient. And this is what defines the Laplacian. So really, we can take the minus sign out of the divergence because it's a constant and put it right here. So let me just do that. And well, this is just the Laplacian. So really what we have is that the Laplacian of this is nothing but this. I'm sorry it's a bit messy, but this is just a really quick derivation. Everything will be much more organized afterwards. So well, this is actually not what we have here because there's some charge density. This is what's known as Poisson's equation, and if you want to know how to solve it using Fourier transforms, you can have a look into my channel because I did a video on that. Well, in our case, what we have is that there is also no charge density. We're assuming a region of space where there is no charge density. So this would go to 0. So we will end up with this equation. If there's no charge density, no magnetic field, and no conducting current, and so on, we get to Laplace's equation, which is an electrostatics approach, an electrostatics problem. Now that this is out of the way, let's just see how do we actually solve this equation. Well, usually partial differential equations and ordinary differential equations even are really hard to solve because they get really tricky and real complicated real fast. But in this case, we can actually do it if we take into consideration some assumptions. What we usually do with differential equations is to consider some assumptions and say, well, maybe I want a solution that has this form or a solution that has these properties, and well, from that we can actually get working. Here it will be really hard to just say, well, what is the general solution? I don't know if we can even do that. What we can do is to say, well, I am going to assume that the solution has a certain form. Or rather, more accurately, I am going to look for solutions of a certain type. So in our case, we are going to do what's really common to do in partial differential equations, and that is to assume a function of this type. We are going to assume a function that is separable. That is, it can be split up into a function multiplying another function. And let me just explain real quick because this might seem very arbitrary. We are working in spherical coordinates. This means that we have some kind of spherical symmetry. So this is y. So we have some kind of spherical symmetry. That's why it's nice to go to spherical coordinates. And spherical coordinates, well, they take us from x, y, z to r, theta, and phi. Phi is just this angle, and let's just say that we want to go to this point here. R is the radius, the distance to the origin, the radius of the sphere, and theta is just this angle. Now, how does this help us? Well, we are going to assume in our problem that we have axial symmetry. That is, that the problem looks exactly the same, or the problem looks exactly the same, or the potential rather looks exactly the same if we do revolutions about phi. That is, the potential does not depend on phi. So it doesn't matter which angle phi we have, or where in these positions we are, like where in our phi we are moving, we are going to end up with the same potential. Okay, that's what we're going to assume. So what we're going to assume is that phi doesn't depend on phi. Depend on little phi. Okay, that is what we call axial symmetry. In that case, we can write that phi is just a function of the radius and the azimuthal angle. Well, some people might call this the azimuthal angle, but well, I'm going to call this angle the azimuthal angle. So this is what we want to look for. We want to look for solutions of this type. But not only that, we want to also look for solutions that are easy to find. And really easy solutions to find are these ones right here, where we can separate the dependencies. That is, we can write this function, which depends on r and theta, as a multiplication of a function r, which only depends on r, and a function t, which only depends on theta. Why should we do this? Why is it important or useful? Well, the thing is that by doing this, we convert this partial differential equation problem into an ordinary differential equation problem, which might be easier to solve, and in fact it is. So that's what we're going to do. We're going to propose or assume that we're looking for solutions of this form, okay? Where capital R is just a function that only depends on the radius, and theta is a function that only depends on, on theta. And well, to describe a circumference, well, let me just say that the radius is going to go from 0 to some, I don't know, what do we call it? Let's just call it R0, and this is a radius, and that theta is going to go from 0 to pi. If you want more details about spherical coordinates and cylindrical coordinates and in general different curvilinear coordinates, just look into my channel because I will have some videos about it. Now, well, let's just get on with the problem. What we have is the Laplacian of capital Phi of R. And we are assuming that it has these kinds of solution. So let's just apply the Laplacian operator on spherical coordinates. And we get that, well, 1 over r squared and the partial derivative with respect to r of, well, r squared times our function. What is our function? I think I made a mistake here. Should be partial derivative with respect to r times our function. Now it makes more sense. It didn't make any sense before. So just a quick fix here. I forgot to write this partial operator here and this one right here. So let me just write this. So just bear in mind that multiplying this r is a partial differential operator, and likewise here. So r squared times the partial derivative with respect to r of phi, let me just leave this space here, plus 1 over r squared sine theta, and partial derivative with respect to theta of the sine of theta, and here we'll multiply by the derivative with respect to theta. And you could say, well, what about this term? We don't actually need that term because we said that phi does not depend on little phi. That is, the partial derivative of phi with respect to phi is 0 because it doesn't depend explicitly on it. So likewise, the double or the second partial derivative is also 0, so this goes to 0 and we don't need it. So this is what we have. And well, let's just plug in our function, and our function is r and t. Now, partial derivatives act only on functions which depend explicitly on the variable we're taking the derivative with respect to. So, given the fact that t theta only depends on theta and doesn't depend on r, it can actually come out of both derivatives. And we end up with this. Up with 1 over r squared t theta, okay, comes out of both derivatives, times the partial derivative with respect to r. Let me just write this here like this. Yes. Why have I changed this partial derivative for this regular derivative? Well, the thing is that the partial derivative here and the regular derivative here coincide because r does only depend on one variable, and that is r. So we can actually, instead of writing this, we can just write the derivative with respect to r. Likewise, here we only have a function that depends on r, so we don't need a partial symbol here, we only need a regular derivative. Now, the second term, the same happens. R does not depend on theta, so it comes out of both derivatives. So we have 1 over r squared sine of theta and r. R, yes. And well, again, instead of a partial derivative, we have regular derivatives. And this is just the sine of theta, and again, the derivative of this function with respect to theta. And this is equal to 0. This is what we have so far. What can we do from now? Well, of course, we have assumed that r is not 0, so let me just correct this for a minute and say that we're not actually considering the point 0 because it's a conflict point and we don't want to deal with it. So what are we assuming here? Well, then our next assumption is that neither r or t are 0. Why? Well, because if r was 0, phi will just be 0 and we already have our problem solved. And if t was 0, likewise, we will have our problem solved. So we are assuming that r and theta are not 0. What does this mean? What does this imply? Well, this implies that we can actually divide everything by both quantities because they're not 0. Nothing will blow out to infinity. So if you just let me erase this for a minute, we have that. Yes, well, let me just erase everything. What we have is this equation right here. We can rewrite this equation by dividing everything by t and dividing everything by r. What we would get is, and also, we can multiply everything by r squared. Just notice that if we multiply all of this by r squared and all of this by r squared, well, this is just 0. And this, well, this cancels out with this one, and this cancels out with this r. So we are left with no r's, no r squares on the bottom, on the denominator. Now, if we divide by t and divide by r, what we get is this. Well, here we divide by t, so there is no t. Derivative with respect to r of r squared, the derivative of r with respect to r. But we have also divided by r, so we have to multiply by this. So 1 over r. Plus, well, we don't no longer have this r, but we have this t, which has come on dividing. So we have, let me just write this here, 1 over t times this derivative. Derivative with respect to theta of the sine of theta times this other derivative. And this is equal to 0. So, well, before I erase, just notice again what we have done. We have multiplied by r squared, cancelling out these r's, and we have divided by t. Okay, this no longer has a t, and this has a new t on the denominator, and well, that's just 0. And we have divided by r. No r's here, but 1 r dividing here. And again, just 0. So let me just erase this. Okay, what can we do from now on? Well, I just want you to notice one thing, that we can rewrite this equation as follows. We can take all this to the other side as with a negative sign, so this would be just like this. Okay, we have just taken all of these terms to the other side. What do we have? We have a function, let's just call all of this little f of r, and this is equal to, well, all of this is just little g of theta. Does this make any sense? Can a function that only depends on r be equal to a function that only depends on theta? Well, they can, only in one scenario, and that is that they are constants. This doesn't imply that they have to depend explicitly on r, but rather that we are seeing as a function of r. So if this depends explicitly on r, this equality doesn't make sense because this does not depend on r. And likewise, if this depends on theta explicitly, this wouldn't make any sense. So the only possibility is that both of these things, both of these functions are a constant. So this has to be a constant, and this has to be another constant, which is the same constant, okay? And let's just say that it belongs to real numbers. So these are our constants. This is what happens. So we can just write, well, if this is equal to this and they both equal to a constant, let me just write that they're equal to, what do I call it? Let me just call this K instead of C. So that's what we get. We get that this can only happen if they're equal to a constant K, which belongs in the real numbers. Notice that now we no longer have partial derivatives. We don't have a partial differential equation. We have reached our goal, and that is to express everything in terms of ordinary differential equations with ordinary derivatives. So we can split this into two differential equations. This one, right? Let me just write it here. The derivative with respect to r of r squared times the derivative with respect to r of our r function times 1 over r. And this is equal to, well, this is equal to k, so it's just equal to k. This is our first equation. The second equation, likewise, is just expressing this equal to this new constant, and, well, let me just write this like this. Sine of theta and our derivative. And this is just, well, minus k t theta. I just multiply by t on both sides, and likewise I'm going to do it here. I'm going to multiply by r. I'm just going to write k times r. So we have these two ordinary differential equations. How do we solve them? And why have I written here Legendre's equation and Euler's equation? Well, the thing is that when we expand this, we're going to see that this is actually an Euler type ODE, and this is a Legendre type ODE. This might seem a bit harder to notice, but you see how it is actually just a Legendre ODE. So let me just expand this a little bit. How do I organize this? Yes, let me just expand this one. So first of all, we're going to look at the function in R. We're going to find R, solving this differential equation. And let's expand this. Well, this is just taking the derivative here. This is just 2R, R prime. Notice I'm writing a prime to denote the derivative with respect to R, plus R squared times the double derivative with respect to R, and this is just KR. Let me just check for a minute. Yes. So we can write this a bit better. We can just say that, well, this is just, well, let me just 2R. This is just R squared, R double prime, plus 2R, R prime, R. Was it plus or minus? Plus, minus KR. And well, this is our, let me just write this a bit better. This is our first ODE that we have to solve. And the second one, I'm going to write it down here so it doesn't bother us too much. But don't focus on it now, it's not really well written, it's just here so I can remember it. So I'll just erase this. So what is this? This is an Euler type ODE. Notice instead of y we have r, and instead of x we have little r, but otherwise it's just the same. X squared, in this case r squared times a double derivative plus 2 alpha x, well, in this case alpha is 2 and x is r, y prime plus beta or beta times y. So in this case what we have is that alpha is 2 and that beta is just negative k. That's what we have. Now in order to solve this, we would actually want to know what k is. I'm going to do a quick heads up, and I'm going to say that k, well, we're going to write k like it follows, as n and n plus 1. This is arbitrary. This seems really arbitrary. You might be thinking like, why are you doing this? This is so arbitrary. We will see afterwards that even though it's arbitrary, it's really nice to express this constant like that, because it will actually help us a lot with Legendre's equation. Well, for now, let's just assume that we are Legendre or Euler and that we come up with this variable real fast. So how can we keep on going? Well, what we usually do with Euler equations is we propose a solution, and in this case, the proposed solution is a solution of the form r is r raised to some power n. Yes, let me just call this power n, where m is a real number. All we have to do is to find m. How? Well, we substitute into the equation. We have r squared times, well, the double derivative of this is just m, rm minus 1, taking derivative again, just n times n minus 1, rn minus 2. Well, now we just add 2 r times, well, the first derivative is just n times r raised to the n minus 1 power minus k. Let me just keep writing k, afterwards I'll do the change, times rn, and this is 0. Well, if we multiply this and this, we get, well, n minus 1 r to the m plus 2m r to the m minus k r to the m and 0. And assuming, as we said, that r is not 0, it never is 0, it doesn't reach 0, we can divide everything by rm and get that rm, or coefficient, or exponent, is given by this equation. And this is what's called the initial equation, and this is precisely, I don't know where I read, this is precisely this equation right here. Notice that alpha in this case is 2, and that beta in this case is negative k, just as we said before. So this is where this equation comes from. It's just by proposing this kind of solution, well, then just substituting. And this will give us our coefficients. Now, to solve this, well, let's just use a regular quadratic formula, right? A regular quadratic formula just tells us that m, let me just write it like this, that, well, we can expand this m squared minus m plus 2m minus k is just m squared plus n minus k, and this is equal to 0. With our quadratic formula, which we learned in primary or high school, we have that m is just minus 1 plus minus the square root of 1 minus 4 1 times 1 times minus k over 2 times 1. Now we will write k in that form that we suggested. We have minus 1 plus minus the square root of 1 plus, notice this negative sign goes with the other one, becomes positive, and we have 4 times n and n plus 1. Well, let's just expand this, it's just 4n squared plus 4n, so this is just 4n squared plus 4n over 2. What can we do? Well, this is a perfect square, So we can just say that we know that 2n plus 1 squared is just 4n squared plus 2n plus 1. Sorry, this should be a 4n because it's 2n times 2. Well, this is what we have here. So instead of this, I'm going to erase it and rewrite it in a quadratic form, which is 2n plus 1. The square root cancels with the square, leaving us with an absolute value, like this. It leaves us with the absolute value of 2m plus 1 over 2. I'm sorry, this should be an n, not an m. N, no, don't get mistaken with this n. Yes, an n. Well, we cannot keep on going from here until we know something else about n. And we're going to assume something about n. We're going to say that n is just, it goes from 0, 1, 2, n is just a positive or non-negative integer. It's just like this. This is what we said we want to assume, and that's what we want to assume. Just notice that this k actually is just this, surprise, that's why we chose it. So what? Our n is just going to be a non-negative integer. Well, in that case, this absolute value is no longer needed because this will always be positive. And this leaves us with two solutions. The first solution, I'm just going to call it, let me just write it like this, n1 is just, well, negative 1 plus 2m plus 1, this cancels out with this one, 2n over 2 is just n, so n, well, our other solution is just n2, which is just minus 1, let me just write this like, oh sorry, I should have included a parenthesis, not just taking out the absolute value, oh well. Minus 1 minus 2n, minus 1 is just, well, let me just write it more explicitly, minus 2n minus 2 over 2 is just minus n plus 1. And this is our other solution. Surprise, surprise. This is actually a really nice solution. Wait a minute. Negative sign. Don't forget the negative sign. Well, this is what we have. We have already solved our Euler type ODE. And I will write this result just right here. But before, let me just erase. So our solution, as we said here, is just of the form some constant times our first root plus some other constant times our second root. We have that r is just some constant, let me just call it c1, times r raised to our first root, which is n1. But what is n1? n1 is just n. Plus some other constant times r raised to our second root. And what is our second root? n2, which is negative n plus 1. This is our first solution. This is the expression for r. I'm just going to write here. And this is, just write it. This is just c1 r raised to the n plus c2 r raised to the minus n plus 1. Now, all we have to do is to solve this other equation that I wrote down there. So let me just erase this. So see, the video might be taking a bit long, but that's just because I want to explain everything really slowly and let you guys have time to sink everything in. I almost fixed that. So this could be done much faster if you already know exactly what you're doing, but for now we just want to understand everything we're doing. Now we have to find our solution t theta. Well, to find it, we just have to solve that equation. And let me just expand it. So the derivative with respect to theta of this is just, well, the derivative of the first, which is just the cosine, times t prime plus sine, we're not taking the derivative in that term now, times t double prime. And this is equal to minus k, which are constant, times t. just like before, we are going to write it in a descending order, right? So let me just write it like this. So t double prime times our sine plus t prime times our cosine is equal to minus k and I just realized I forgot one term. And that one term, if you were cautious enough, you might have noticed that, well, there's this missing here, right? That's missing there. I just forgot when I multiply by r squared, I think I cancelled out this sign too. I'm sorry, it's just things that happen, but that's for you to keep awake. So that I forgot that. So multiplying by that, we actually have this. So that's what we have. Really sorry for that mistake. I didn't realize until I was expanding this. So sorry for that. Well, let me just check for a minute and we'll keep on going. Yeah, so that's it. So we have expanded it, included this missing term, and that's what we have. I said before, a while ago, that this was actually Legendre's equation. It's more dressed up, it's more, it has a costume on, but it's actually just Legendre's equation. How do we know it? Well, usually what we do to reduce an equation to another kind of equation is to make a change of variables. And in this case, the smart change of variables is u equals cosine of theta. But before, let me just remind you about Legendre's equation. So we have a double derivative times this term plus a derivative times this term plus this and everything. Well, what actually suggests us that this might be a Legendre differential equation is that, well, if we write k, as we said, n plus 1, n times n plus 1, well, we might be able to work things around so we can get to this expression. And how are we going to do it? Well, we're going to say that we're going to make this following change of variables. Notice that when making change of variables in differential equations, you have to have really present the chain rule. If you know what the chain rule is, just go on my channel, I have a proof on it, and it's actually a really fun proof. But well, you have to have it really into account, and we're going to see how we do it. So first of all, we're going to propose or make this change of variable u equals to the cosine. Why? Well, this leaves things really easy, and it's what's usually done. You could try some other change of variables and see if you can get to somewhat closer Legendre equation, or if you can solve it in another way. But the usual procedure is to use this substitution. Well, how do we keep on going? Well, we have that our original function was t of theta. Isolating theta here, and assuming that we can take the r cosine and everything. Theta is just the r cosine, and I'm using this notation. This is not 1 over cosine, this is just arc cosine. Let me just topic confusion, arc cosine of u. So t theta can actually be just written as t of, well, arc cosine of u. But this is a function of u. I'm going to just say that, well, this is just f of u. Just notice this. We have a function on theta, and by making this change of variables, we actually get another function on u. Okay? What's next? Well, we have this, we have t of theta, we have the cosine, we don't have the sine. Well, how do we find the sine? Well, from the fundamental equation of trigonometry, we know that the cosine squared plus the sine squared is just 1. Well, this is just the Pythagorean theorem on the unit circle, but well, we see that, well, the cosine of theta is just the square root of 1 minus the sine square of theta. And we said that the cosine was u, so u is that. So let me just write, where should I write it? Oh, I just write it here. That u squared, taking the square root on both sides and assuming well, not assuming anything, just taking the square root, 1 minus sine squared. And yeah, that's what we get. So what's the next step? So we have everything written down except for t prime and t double prime. So what is t prime? Well, t prime of theta is just a derivative with respect to theta of this function. As we said earlier, this function can be thought of as another function in U, because we have made this change of variables. So by making this substitution, we say, well, this is the same as f of u. But what is the derivative with respect to theta of this? Well, we have to think backwards and say, well, u is equal to the cosine of theta, but u is a function of theta. So let's just say that it is g of theta. This is how you have to think about it. You have to say, well, this is a function of what? And when I'm taking the derivative, which is a function of what? And you see that applying the chain rule is really easy. Let me just say that, well, the derivative with respect to theta, and you see it really easy this way, it's just the derivative with respect to theta of f of what? Well, of g of theta, because u is just a function of theta too. So of g of theta. Applying the chain rule, we take the derivative with respect to g of theta, that is the derivative with respect of f with respect to g of theta, with respect to what? To g of theta. This might seem somewhat of an absurd notation, but I'm just to I'll tell you what this exactly means. Times the derivative of g of theta with respect to theta. And let me just erase this because we no longer need it. I think I have to clean already my eraser again. Well, the thing is that the chain rule tells us that if we have a composition of functions, the derivative with respect to x, or let me just say with respect to with respect to gamma, I don't know, of f of g of gamma, this is just the same as we have. Well, we have to take the derivative with respect to the inside function, and then the derivative of that inside function with respect to the variable. So this would just be df dx, but instead of x, we're changing it for gamma. Well, maybe this is getting too messy. Well, let me just explain it in a different manner because I don't think that's the easiest way to understand it. So this notation just means the following. This just means that we are taking the derivative of f with respect to x, but instead of f being a function on x, it is a function on g of theta. Okay, so instead of x, this is what we do. So what does this mean? This just means that, well, just consider f of x, take the derivative, the regular derivative with respect to x, and all afterwards just change x by g of theta. And then all of this is multiplied by the derivative of g of theta over theta. Well, this we can just say that this is f prime of g of theta. But what is g of theta? It's just u. Let's just say that it's u. G of theta is just u. Okay, and even it would be easier here to say the derivative with respect to u. Right? Say that, well, instead of g of theta, we can actually just have called it u. Sorry for that messing around with your heads, but you can just call it u. Why not? U of theta. So really, it's just f prime of u times, well, the derivative of g of theta with respect to theta is just the derivative of this with respect to theta, which is minus the sign. So we have minus sign of theta, and well, that's it. T prime is this expression. I'm just going to use the other one. I'm sorry for that. Maybe I got you more mixed up than I would have if I hadn't explained things so much. So I hope you're not too confused, because it's not too hard to follow this. It's just you have to get used to it. So negative sine of theta times f prime of u. Let me just keep this here. And now, what do we do now? Well, we have to use the derivative again to get t double prime. So just like before, we have a t double prime of theta is equal to the derivative with respect to theta of t prime. And what is t prime? T prime is this, so let me use, instead of this, write minus the sine of theta f prime of u. And this, well, applying the multiplication rule for derivatives, this is minus the cosine in the derivative, minus the cosine of theta, f prime of u, and, well, again, minus the sine, times the derivative with respect to theta of f prime of u. Just like before, how do we confront this? What we have to think is that, use this color, what I have to think is that, well, the derivative, let me just write it here. The derivative with respect to theta of f of u prime is actually this. U depends on theta too, so we have to apply the chain rule. How? Well, we take the derivative of f with respect to u, and then the derivative of u with respect to theta. And in our case, well, in this case, it should be f, it should be f prime. And this is a function of u. So we have f double prime of u times this term here. And this term is just, well, derivative with respect to theta is just negative sign again, minus sign. That's what we get. So, plugging this into this part, we get, well, this actually becomes a plus, minus times minus becomes a plus, and this is a sine squared. And this is just f double prime of u. So this is t double prime. And we are actually done with the change of variables. We only have really little to do left. We only have to plug all of this information on the original equation and see where the magic happens. So, to make more space, I am going to write these results here. And what are the results? Well, the results are that u is the cosine of theta, that u squared is 1 minus the sine of theta, and raising this, that t is f of u, that t prime is, what is it, minus sine times f prime, and lastly that our t double prime is this expression. Well, what is this expression? This is just t double prime theta, and it's sine squared f double prime of u minus the cosine of theta f prime of u. Just check for a second, and yes, that's right. So that's what we have. So you see, it's the thing is that none of both these equations were too long to do, but when you have to do both of them at the same time and explain it actually every step, the video can get really long. Notice there's actually nothing too hard, and if there are any questions, just ask me in the comments or whatever. So, and this is just theta. Slightly better, and that's what we have so far. Just plug that into the equation and see what happens. Well, t double prime is just sine squared f double prime of u, and well, before anything, let me just separate it like this. minus f prime of u. Well, this is all multiplied by sine, isn't it? So okay, what we have now is that, well, instead of sine squared, what we're going to write is 1 minus u squared. So 1 minus u squared. And here, instead of our cosine, we're going to write just u. And instead of sine, we're going to write, well, let me just keep writing sine here. You see why? I think. Maybe I made some mistakes here, I'm not too sure now. So the cosine, again, is just u times t prime, or t prime is just minus sine of theta, f prime of u. Oh, yeah, sorry. Well, let's just change it. This sine is just 1 minus u squared. And this sine here is just 1 minus u squared. And likewise, this negative sign comes in front. Let me just check for a second, because it's many things, and maybe I have gotten mixed up with something. So we had our t double prime there, negative u, and the sign is just 1 minus u squared. Yeah, cosine is u, and t prime is just minus the sign. Okay, it seems fine. Well, passing this to the other side, we get plus k, and t is just f of u times our sign, which is 1 minus u squared. What do we have? We have that, of course, assuming that this is not 0, assuming that 1 minus u squared is not 0, meaning that u is not plus minus 1, which is the same as saying that cosine of theta is not plus minus 1, which is the same as saying that theta is not an integer multiple of pi. But well, here we said that it is. Well, let's just change that so we can divide. Just consider this. Just making things a bit easier for us so we can divide. So this is what happens. We can actually now divide. And well, 0 should actually be another problem. So let's just again get rid of 0. Just keep it like that. So we can actually divide because theta is not n pi, and yeah, we can divide by it. So this, and this cancel out. Well, we have the following equation: 1 minus u squared f double prime of u minus u squared, and well, yes, minus u f prime minus u f prime again here, plus kf. Well, this just becomes minus 2 u f prime plus kf. But let me just express, sorry for erasing so much, let me express k as we said that we wanted to be. So n plus 1 f of u. This is equal to 0. This finally is Legendre's equation here. Instead of x we have u, and instead of y we have f, but this is exact same relation. What is the solution? Well, again, we're expanding it around x equals 0, and we're assuming, as we said before, that is 0, 1, 2, and so on. And our solution is actually that f of u is Legendre's polynomials evaluated at u. But, well, we actually wanted to find t theta, but f of u is just t theta. So we have actually found t theta. And we'll just, for the sake of it, what is u? U is just the cosine. So really, we have Legendre's polynomial with the cosine inside. Seems weird, right? This doesn't seem too common, right? It is actually really common, but seems weird at first. Why? Because instead of an x, we have a cosine here. So in all of these Legendre polynomial formulas, the Rodrigues formula, instead of x, here we will have a cosine. It might seem weird, so what we actually do is, as I said before, just evaluate it with x, and after we have taken the derivatives of the sum or everything, change the x by a cosine. So that's what we get. So let me just write this here. T is just Legendre's polynomial evaluated at the cosine of theta. Notice one thing, or well, quite some things. Here we don't really have one solution because we have a solution for each n. So really we should write here n. Likewise here we don't have a simple solution. We have a solution for each n again. So that's what we have. So we actually don't have just one solution, but an infinite set of solutions composed by R0, T0, R1, T1, and so on. And we'll see afterwards how this works. So, yes, let me just erase everything and we'll do a quick recap of everything. Well, yes, before anything, we were able to solve this equation, or to assume it, because u, in this case, instead of x, was not between, was not -1 or 1. So it was between -1 and 1. As we said, the condition that theta belongs to 0 on pi is analogous to the condition that u belongs to -1 and 1. Because, well, theta just goes from 0 to pi. Okay? Hope that's clear. So erasing this, using our results, we can get the solution. So our potential, we said that we wanted it to have this form and to satisfy a Laplace equation. After all of these calculations, we see that we have found a solution. But not only one, but rather I'm just going to write here n, because we have a solution for each n. And this is, well, let me just make some more room. This is phi n. Well, it's just r n times t theta n. In our case, well, let me just C1 Rn plus C2 r to the minus n plus 1 times, and let me just write this, I have no space, times this. And really here, these constants are not the same for each solution, so they should have another subindex here. But because there are many subindexes, instead of that, I'm just going to call this constant an and this constant bn. This is a solution to Laplace equation. Try it out, calculate the spherical Laplacian, and see if it actually gives you 0. But we can do better. We know that a linear combination of particular solutions is a solution too. And in this case, they are linearly independent. I'm not going to prove it here or derive anything, but these phi n are linearly independent, which means that we can construct the most general solution in the following form by just taking the sum of all of them, a linear combination. But as we said, n is 0, 1, 2, and so on. It goes to infinity. There are infinite solutions. So how do we make a linear combination of an infinite set of solutions? What we do is, well, just like before, instead of taking a sum, a finite sum, we take an infinite sum. So we have that the general solution is, instead of r, I'm just going to write r theta because it depends on r and theta only. Well, this is just the infinite sum going from, let me just say that n goes from 0 to positive infinity, right? Because it just goes on and on and on to positive infinity. Of Rn, which is this, an Rn plus Pn r minus n plus 1 times our Legendre polynomials, which is this. And well, we are actually done. Let me just write this here. Again, we're assuming that well, r goes from 0 to some r. Let me just change it again and say that well, let's just keep the open interval. Doesn't matter if we close it at r0, but let's just keep it open. And theta just goes from 0 to pi. This could be the electric potential, electrostatic potential in spherical coordinates by using Laplace's equation. This should be Laplace's equation, the solution to it, in spherical coordinates. Assuming, as we said before, axial symmetry. That is, well, we're assuming axial symmetry. As it doesn't depend on phi. So the derivative of phi with respect to little phi is 0 because it doesn't not depend explicitly on it. Let me just rewrite this a bit better. So well, I know it might have been kind of a long video, but well, I hope you liked it, that you found it interesting, and you learned something, and well, if you want more details, just look into my channel, and well, yeah, that's it. So see you in the next video.